Hello again to our lecture series on the finite element method. And this week will be the first of two more theoretical lectures. And the topic is, the question, does that even work? So we are talking about solution theory for our linear partial differential equations. So we want to answer the question, does a particular partial differential equation have a solution? Is the solution unique? And all of those questions. And the outline for this, as usual, we start with a short introduction and what can go wrong. So I want to show you how easily it can happen that we change one of our commonly known problems to something that causes trouble. Then we give some mathematical preliminaries, short recap on Sobolev spaces, and then we look in particular on the Hilbert spaces that are interesting for us, talk about norms, bilinear and linear forms. Then the big result of today that is important is the lemma of Lax-Milgram. We formulate it, and then we talk about implications, summaries, and how is it helpful for us. And in the end, that's probably the most interesting part. How does it look if we use Lex-Milgram's lemma for our purposes of finding out solutions for partial differential equations? And we do this with the help of two examples that you have seen before. One reaction diffusion problem and Poisson's problem. So nothing new there. But you will see how differently they behave, and you will also see the reason why, in this case, I have started with the reaction diffusion problem and not with Poisson's problem. Also, another remark about the lecture today, the format will be slightly different in the sense that most of the lecture will be using handwriting. The reason for this is that I have personally decided that if we're talking about more mathematical concepts, it's a bit troubling if you just see a new slide popping up and you're overwhelmed with the contents and the many formulas and so on. That's why today we want to develop all those concepts together in the sense that I will create the slides by handwriting while giving this lecture here. So let's get started with this. Okay. The introduction starts with the question, what can go wrong? And for this we go back to the roots to our most simple problem that we have discussed in this semester, Poisson's equation minus Laplacian of u equals f in omega. And this is just the PDE, and there is two different ways how we can equip this with, there is more different ways, but there is two fundamental ways how we can equip this PDE with boundary conditions. The choice that we have used in most of the semester, for a good reason, as you will see later on, were Dirichlet boundary conditions stating the values of your function on the boundary. But also we have mentioned multiple times there exist different types of boundary conditions, and the other famous choice are the so-called Neumann boundary conditions, where we state something about the derivative in normal direction on the boundary. For example, a Neumann boundary condition can be an homogeneous one, saying that the gradient of u times the normal of the domain is just 0. And of course, the outer normal is something like this. And then this boundary condition here states that a so-called no flow is happening. So none of the quantity u can diffuse out of your system. In technical terms, this would mean something like an isolation. So if you think about, for example, a rod that is being heated, then this Neumann boundary condition tells you something like it is insulated on the boundaries such that no heat can go out of the boundary. Okay, so both of these choices are intuitively very clear what they are doing. And while the Dirichlet boundary conditions are talking about function values, the Neumann boundary conditions are saying something about derivatives. And to make this a bit easier to understand, you could always think about a one-dimensional example. So if your domain omega in 1D is just an interval, then, well, the Dirichlet boundary conditions say something like u of 0 is, let's say 10, and u of 1 is 20. And then if you want to talk about Neumann boundary conditions in this 1D case, this would be u prime of u is something and u prime of 1 is something else. Okay, so the difference is, in one case you're talking about function values, in the other case you're talking about the derivatives. Okay, and now let's make it a bit more precise. If we choose f equal 1 and then talk about homogeneous Dirichlet and Neumann boundary conditions, so in one case just 0 function values, in the other case 0 flow across the boundary, then on the left hand side for the Dirichlet problem you see, just as usual, your typical bulb-shaped solution. So you have clamped your membrane on the boundaries and you're pushing with a constant force and you get this result. So that's nothing spectacular. But what's interesting is, if I do that same thing with the Neumann boundary conditions, my result looks totally terrible. And not only does it look flat, which is not very likely to happen for a membrane, also if you look at the function values here, then you see that this whole solution has something like values in the range 4 to the power of 4 times 10 to the power of 13, which plain and simple just means the solver couldn't find a solution. So there is no solution to the linear system. And yeah, what happened here? Well, the answer to this question is as simple as it is complicated. We tried to solve something with a FEM that does not even have a solution. And that's the whole topic of today, to analyze how we can find out if something has a solution. But as a start, we want to be a bit more specific on, to give you an intuition how this problem looks and what went wrong here. And for this, I'm starting with a simple one-dimensional example. So I'm writing down Poisson's equation in 1D that reads minus u double prime of x, and I'm using again my constant right-hand side 1, and my domain is the interval from 0 to 1. Okay, and then let's start with the Dirichlet boundary condition. So u of 0 equals u of 1 equals 0. Okay, so that's just Poisson's equation with homogeneous Dirichlet boundary conditions in a 1D example on the interval 0, 1. Then, well, of course, this is a super simple example, so let's just solve it. What do we do? Well, we start off by integrating, right? So if you have something classified as a differential equation, then you can just integrate, because on the right hand side you don't have u occurring here, so it's essentially just integrating. Integrating once gives you something like minus u prime of x is the integral over 1 plus some constant alpha, right? So you have to integrate this thing and you get one constant, because the constant would vanish in the integration, in the differentiation process anyways. That is, you have here x plus alpha, right? And then if you would integrate this for any arbitrary alpha, this would give you the 1. Okay, this is good and well now, and then we go for one step more and integrate again. And then we have minus u of x is, well, the integral of this, so the integral of x plus alpha, plus some other constant beta. And that is just minus 1/2 x squared. That comes from integrating x again. Then you get alpha times x, that is from integrating alpha, and that is plus beta. Of course, you could add a third constant from the integrating process of alpha, but that doesn't really make a difference, because, well, if you have 3 constants, one of them would be, can simply be added to the other. So in total, by integrating twice, we get 2 constants that we can choose. And how do we choose them? Well, we choose them using our boundary conditions. So we arrive at the formulation u of x is, and now I'm taking the minus here from the left hand side to the right hand side, and minus 1/2 x squared plus alpha x plus beta. Okay, now let's plug in a boundary condition, and we start by plugging in the left hand side boundary condition. Okay, so C u of 0 equals 0. Well, let's see. Well, if I take this formula and plug in the value 0, then this is minus 1/2 times 0 plus alpha times 0 plus beta. So if that thing is supposed to be 0, we can directly conclude that beta has to be 0, because, well, the rest is just 0. Okay, so we come to the point that u of x is minus, and then 1/2 x squared plus alpha x. And then number D, you plug in the other boundary condition, u of 1 equals 0. And then you get u of 1 is now minus 1/2 times 1 squared plus alpha times 1. And then if this is supposed to be 0, you can pretty easily conclude that alpha has to be minus 1/2. And that gives you, in total, u of x is minus 1/2 x squared minus 1/2 x. Then you can plug this in. If you differentiate it twice, you get u double prime of x is 1, or minus 1, which is exactly the partial differential equation. And also, if you plug in 0 here, you see directly that this gives you 0. And if you plug in 1, you arrive at minus 1/2 minus 1/2. So you get also 0. So that is perfectly fine. So we've seen here that in the simple case in 1D, for Poisson's equation with homogeneous Dirichlet boundary condition, we could compute a unique solution. So there was nothing to be arbitrarily chosen. We just could directly compute the solution. Now let's try to work on the other problem. So now let's say we are still talking about Poisson's equation, still talking about the same domain, but now instead we want to do something with Neumann boundary conditions. So we say that u prime of 0 is u prime of 1 equal 0. So this is homogeneous Neumann boundary conditions here in 1D. And well, the first few steps are exactly the same. So a plus b are done exactly the same because you're still integrating twice. You get those two constants, alpha and beta, that you can choose. So you again arrive at u of x is minus 1/2 x squared plus alpha x plus beta. And now you again need to do the process of using the boundary conditions to determine your your coefficients alpha and beta. Then let's do this. Let's take this function now and compute the derivative, because the boundary conditions are talking about derivatives. So u prime of x is now minus x minus alpha. So yeah, I took this 2 with the 1/2, that gives me minus x, and then the minus and the alpha. And already here you can see why we have a huge problem. This thing here, this derivative of u, has exactly one thing that we can freely choose, and that is the value of alpha. But we want this to fulfill boundary conditions on both sides. Okay, let's try to make this work. Let's say we start on the left-hand side. Let's say we start by claiming that the derivative on the left-hand side is supposed to be 0. Then this means u prime of 0 is supposed to be 0, so u prime of 0 is minus 0 minus alpha. Okay, well, if that is supposed to be 0, we can conclude that alpha needs to be 0. So our function looks like this. U of x is minus 1/2 x squared plus beta, because the alpha part vanishes. And you see here now that this is quite a lot problematic, because now we can't choose anything else, because the alpha has been chosen such that it fulfills the left side boundary condition. And the beta, well, that doesn't do anything good for us in terms of the boundary conditions with the derivatives, because it vanishes anyways. But now we could, of course, try out if this function fulfills the boundary conditions. Maybe we would be lucky. So u prime of 1 is minus x. And okay, this minus x does probably not fulfill our boundary condition. Because if I plug in, okay, well, that doesn't really make sense. So let's, that's minus 1. So, yeah, and that's not 0. So you see here, if we do the Neumann problem, already in this simple one-dimensional example where we could compute everything analytically, we see that we don't get a solution. It just doesn't work. And of course, it's not always that simple, but the task for today is to get a mathematical setup that we can check whether or not a problem has a solution. So let's dive in here now. Firstly, we need some preliminaries in order to discuss the concepts of today. And for this, we start reminding us of the Sobolev spaces that we have been discussing. So we talked about this a few lectures ago, and we in this lecture only focus on the Sobolev spaces defined using the L2 norm. So we thought that in general you can use any type of LP norm, but here we only talk about stuff that is derived from the L2 norm. And what's most interesting or important for us are the H1 spaces. So H1 is the space of L2 functions such that the gradient is again an L2 function. So important here, this is the weak gradient. Okay, you always talk about weak derivatives here. And yeah, let's take a quick look what this means. L2 was something like an integral. So if I say that f is in L2 of omega, then this means that the integral over the domain omega of f is less than infinity. Okay, so the integral of f over the domain, of course, f squared here, otherwise it would be L1, not L2. So the integral of f squared is bounded. And then this means that f is in H1 of omega if this is bounded and the integral over the gradient of f. So the weak gradient of f has also to be bounded. Okay. So you see already here that in discussions about these Sobolev spaces, we always have to deal with integrals and with talking about if something is finite or not. And now let's get more into detail about norms. Of course, you probably have remembered from the last lectures or from the lectures in the beginning of the semester that in Sobolev spaces you can always define a particular norm, but we want to go into detail here a bit more. And for that, we start off with L2 of omega. And on L2, the norm is defined pretty simply. And we simply say that the norm, so I always write those double bars, the norm of u in L2. So the L2 norm of U, that is simply defined as, okay, well, here it has to be an integral over omega of U square because it's an L2 function, and then you take the square root out of this. Why this makes sense as a norm is obviously that was in the definition of the L2 space already. So if a function is an L2, if this thing below the square root is finite, so it totally makes sense because this expression is well defined for every L2 function. Yeah, as a quick side remark, if you talk about norms in Rn spaces, so if you talk about the space Rn, which is always composed by vectors of individual real components, so something like x1, x2 up until xn. The norm there, the standard norm that we talk about, the Euclidean norm, is given by the norm of x is the square root of x1 square plus x2 square plus and so on xn square. That's the Euclidean norm in Rn. And if you think about it, this integral here in the definition of L2, an integral is always also some kind of summation. So it's just a sum over all points in the domain. So if you think about U as a vector with infinitely many points, like an infinite dimensional dot vector for all points in the domain omega, then this is the direct transfer of the standard norm in Rn. And if we talk about the weak derivatives also, then we talk about norms in H1 of omega. And there it is not much more complicated. So the norm in H1, so I always write H1 as a subscript here next to the bars. That's, well, we need, of course, some square root. And we can write the stuff that we had already in the L2 norm. That totally makes sense because L2 and H1 are closely related. Every H1 function is also an L2 function. So we can integrate the function, or we can square integrate the function. And we can also square integrate the derivative. So the second part of the definition of H1 was that the gradients, the weak gradients, are also in L2. So this second part here is also finite, and that way this is the direct, intuitive concept for a norm that you would define here. Of course, you can also reformulate this. That's the square root of the L2 norm of U plus the L2 norm of the gradient of U. Okay, that's pretty straightforward. Of course, there is squares here. Okay, one might ask why we are summing up the squares and then taking the square root later on. That question will be answered in a few minutes. Okay, so now we have our Sobolev spaces, in particular L2 and H1, which is the extension of L2 into kind of a derivative concept. And then we have norms on these spaces. Now let's proceed. Hilbert spaces. I have already in the previous lecture about Sobolev spaces mentioned that both L2 and H1, and more precisely all HK spaces, are Hilbert spaces. But here we need more details about this. That's why I want to give a short recap. What does a Hilbert space even mean? So a Hilbert space is a space that is equipped with some scalar product. So the existence of a scalar product on a certain space is crucial to be able to call something a Hilbert space. Again, you can think about the vector space Rn. And for Rn, you know the standard scalar product. So I would call this combination, so this tuple of some space and some scalar product, that's called a Hilbert space, right? Okay, you always need some underlying vector space and some scalar product. And this scalar product of two vectors in Rn is simply defined by multiplying the corresponding components and summing up the whole stuff, right? That's something you all know from lectures you have seen somewhere else. So that's the standard scalar product in Rn. And yeah, that's something you all know. What's important in Hilbert spaces is that the norm of the Hilbert space is always induced. What does that mean? Well, it means that you can define your norm using this scalar product. So in a Hilbert space, the norm always has to be defined as the square root of the application of the scalar product where you put the same argument in both components. Okay, in the following I will always, for a general scalar product, use those angular brackets here. Okay, while the centered dot is only for the standard scalar product in Rn, I will use the angular brackets for any general scalar product. So the norm has to be resulting from the scalar product that you have. Meaning that every Hilbert space is a normed space automatically, because you can directly from any scalar product define a norm. And if you look back at the Rn example, then you see that if you take x times x, then this is x1 square plus x2 square plus and xn square and so on. So if you take the square root of this, then you arrive exactly at the standard Euclidean norm again. So you see here that in Rn, your standard Euclidean norm is induced from the standard scalar product, and that's exactly how you construct them. So that's kind of the idea behind them. Okay, so now if we want to talk about L2 and H1 as Hilbert spaces, we need to do something similar, right? We want to keep it as simple as in Rn, with the only difference that now we're talking about functions instead of real valued vectors. So let's start by talking about L2. And L2 of omega, that's just a side remark because we later on want to just abbreviate it a bit shorter. L2 could also be written as H0 of omega, because H1 is the space of ones weakly differentiable functions that have derivatives in L2. So if you take zero derivatives with the superscript 0 here, that's the same thing. But that's only something we need for later. And well, we know already what the norm is. So the norm is something we have talked about before. So the norm in L2 is the square root of the integral value of f squared. So, well, if you want to construct a scalar product now that induces this norm, the concept is pretty simple. So we take angular brackets of f and g. So we want to define a scalar product on L2 for two functions now. And we want to construct it in a way such that if we plug in f into both components, we arrive at this norm that we have just written down. And what you need to do for that is pretty simple. You need to take an integral of f times g, and that's it. And then you see right away, if you plug in f in both components, that gives you an integral over f squared, so that the square root of the scalar product of f and f gives you your norm. Just a quick question that one might ask about these topics here is this even well defined? So you could be asking if this part here is well defined for every f and g in L2. That's a question we will answer in about maybe 5 minutes. So I need to postpone this a tiny bit. And we can proceed to the case H1. Okay, now we want to do that same thing on H1. And well, what did we have on H1? The norm in H1 was the square root of the integral over f squared plus the integral over the gradient f of f squared. Okay? And now here comes the reason why, that's the question I've been asking before, why we are summing up the squares of the norms and then taking the square root afterwards. Because if you look at this, in order to make it possible to induce this norm from a scalar product, we need this type of structure. Because here now we can simply write down the scalar product of f and g in H1 now, so the H1 scalar product is defined as, well, we take the part from L2 that we have seen already. That's always the case. So always when you write down something for H1, you need to take everything that you know already from L2. And if you define something for H2 or H3, higher order derivative spaces, that's the same concept. You always have to take into account everything that you know for lower order derivatives and then just add something new. So here you have an integral over f times g plus a new integral, and now you need to do something with the gradients. And well, if in the case of adding f twice into the scalar product, you want to arrive at a gradient squared, you now need to take f, the gradient of f, times the gradient of g. And here you also see why I wanted to reserve this dot for the standard scalar product in Rn. In order to be able to multiply those two gradients, which are vectors in the dimension of the underlying space, you still need that dot product. And then you see here perfectly fine if you take the scalar product of f and f in H1, that's an integral over omega of f squared plus an integral over omega of the gradient f squared. And then if you take the square root of that, this gives you exactly your H1 norm. Okay, so the next step now, after having defined those scalar products on L2 and H1 and having seen that the norm is actually induced from this scalar product, we want to find out more about the connection between norms and scalar products. Because while we know that the scalar product of f and f directly defines your norm, we don't really know how the scalar product of f and g relates to the norm of f and g. And because the scalar product itself is derived or induced, is inducing the norm, there has to be some connection. And this connection is quantified in the so-called Cauchy-Schwarz inequality. And I want to first write this inequality down. And maybe you have heard about it already because it exists in all types of Hilbert spaces, also, for example, in Rn. But now here I'm writing down the version that's relevant for us. So let's consider two functions or two f and g elements in hk of omega. And here you see why I wanted to note that L2 is in a sense H0. So this result that we see here is true for L2, for H1, for H2, and for every other H's, for any other Hilbert space actually. So let f and g be in hk. Then we have the inequality that we can take the scalar product of f and g in hk. So again here L2 scalar product or H1 scalar product or something. And then we take the square of this. That also kind of makes sense, because in the definition or in the inducing of the norm, we also needed to take squares and square roots. Then this can be bounded from above by the norm of f squared times the norm of g squared. And what norms are they? Well, these are exactly the HK norms again. Okay, what does this mean in particular? For example, if we look at L2, then this means that the integral over f times g, which is the scalar product here on the left-hand side, and also, of course, you could remove all squares from this inequality and it would still be true, because you can just take the square root on both sides. So this integral over f times g is less or equal the L2 norm of f squared, not a squared, just the L2 norm of f times the L2 norm of g. And that's pretty cool, because now we not only know that the norm is induced by using the scalar product for f and f, but also we know that we can bound this scalar product of f and g from above by the product of the norms. And this also gives you information about the well-posedness of those scalar product, because earlier, a few minutes ago, I've been asking, does it even always make sense to write down this definition of the scalar product of f and g as the integral over the product? And now, with this information, we know that this is well defined, because we can bound this from above by the norm product here. And if f is in L2, then this is smaller than infinity, and if g is in L2, then this is also smaller than infinity, so it's all good. So as soon as you are in L2, this is all well defined. Okay, now after talking about the norms and also the scalar products, we come to a generalization of functions and scalar products, and we talk about bilinear forms and linear forms. Firstly, the simple linear forms. The linear form is a special type of function. So a linear form on the space HK is a function that maps from this space into the real numbers. Okay, so all linear and bilinear forms are real valued. That's very important here. So we get in the end, we get a real number. That's also kind of helpful when we want to handle the results of, or the values of L somehow, because we can do calculations with them just as usual, because they are real numbers. And of course, it has to fulfill properties. The first property it has to fulfill is that L is additive. That's precisely those two components of linearity that you are usually used. So it's additive, meaning that L of u plus v is the sum of L of u plus L of v. And it's so-called homogeneous. That means that you can take a factor, a real factor, out of it. So L of alpha times u is alpha times L of u. And here this is supposed to hold for all u and v in HK, and this is supposed to be true for all alpha in R and u in HK. Okay, so this sounds very theoretical. But yeah, in our cases, if I talk about a linear form, you can always imagine something like an integral. So, for example, a prominent choice for a linear form is to do something like an integral over some function times v. And this looks pretty a lot like our right-hand side of the weak form of the PDEs. And let's look at this precisely. Okay, the input is v. V can be in a value, something in L2, for example. So we can take some L2 function v here, and the result, the integral, will definitely be something real valued, because that's what integrals are doing. They take something from weird spaces and give you a real valued result. And then the linearity, so the fact that this is additive and homogeneous, that results directly from the fact that the integral is linear. So in the following, when I talk about linear forms, you can always think about this example of a linear form. And that's the type of linear forms that we are talking about in this lecture here, because they are the relevant versions for us, because they reflect our right-hand side in the partial differential equation. Now, on the other hand, the bilinear forms, as the name already suggests, they are another type of special mapping, and they take, I'm abbreviating this with a capital B for bilinear. They take two arguments from the space HK and again map into R. And then what they are supposed to be is simply they are supposed to be linear with respect to both arguments. So you could say, so they are supposed to be linear in both arguments. And a good example for this would be b of u and v equal to an integral. Here is again my integrals, because they take stuff from weird spaces and give you something real valued, of u times v. So you simply take your two functions, form the product of them, and integrate over the domain. And yes, this is not a coincidence. This is the L2 scalar product, and the scalar product is just a very special bilinear form. Okay, so every scalar product is a bilinear form, but not every bilinear form serves as a scalar product, because these are not necessarily symmetrical. Okay, so here now we have defined our concepts, and this also kind of reminds us of our PDE cases already, because you can look at this, and this kind of reflects those this weak form of the reaction diffusion problem. We can also have another example. We could also write down b of u and v equal to the integral over gradient of u times gradient of v, and that is just the weak form, the left-hand side of the weak form in Poisson's equation. And that also is no coincidence. That's the reason why we talk about this, because it's possible to capture our weak formulations in the setting of those bilinear and linear forms. And before we can use them for something more, we need to take a look at interesting properties that bilinear forms and linear forms can have. The first interesting property is that they can or should be bounded. Okay, something being bounded is not a very complicated concept. That's something probably everyone can imagine. And here it's important in the following, when we talk about some bilinear forms and linear forms and their properties, we always talk about this on some specific space. Okay, so it's always important to say that something is bounded on a space V, because you will later on see that you can take the same bilinear form, change the space, and some properties don't hold anymore. Okay, well, what does it mean that a linear form is bounded? That's pretty simple. It simply means that you can you can bound L of V from above by some constant that is specific to this linear form times the norm of V in my space. And that's supposed to hold for all V in my space. And here you see intuitively already why it's important to say that something is bounded on V. Because if you change the space, then you will also, of course, change the norm that's interesting on my space. And yeah, then this inequality is also changing. So for example, if you have some linear form that is bounded on H1, so if you say, well, L of V is smaller than some constant times the norm of V in H1, which is the square root of the L2 norm plus the gradient in the L2 norm, both of them squared. So if you know that your linear form is bounded from above by this of course does not imply that L is also bounded from above by just this here, right? So if I remove my gradient part here and just consider the L2 part of the function itself, then we don't know if this is still true. Meaning that if you switch from the space H1 to the space L2, some linear form that was bounded on H1 might not be bounded on L2 anymore. And now for the bilinear forms, it's essentially the same thing, only with now two arguments. So we now say that B is bounded on some space V, more precisely on V times V, but we don't consider any other cases, so we can also say that B is bounded on the space V if this is smaller or equal to some constant CB times the norm of U and the norm of V. So for all U and V in this space. So here again, same thing. This of course depends on the norm of the space that we are in. So both of these are kind of bounds from above. So you see that this is kind of a good property because it classifies that your bilinear or linear form is not exploding. So if the U and the V, so those arguments are in control and not getting too big in terms of norm, then also the resulting values are not getting infinitely large. And the other interesting property is coercivity. And coercive, or sometimes also referred to as elliptic, also on some space. That's a property that you only need for bilinear forms. And in order to define this, we take the bilinear form and insert the same argument twice. Okay, here before we had B of U and V, and now we put in the same argument twice, and then we want to bound this from below by some constant times the norm on the space V squared. And here is important, alpha is supposed to be actually bigger than 0, and 0 is not allowed here. What does this mean? Well, it means that you can not only bound your bilinear form from above if it's bounded, you can also bound it from below if it's coercive or elliptic. This is supposed to be true for all U that are not just the constant 0, of course. And well, if you think about it, if you have something that is bounded and coercive, some bilinear form, then in the combination you can say, let's write this a bit differently, in the combination, this means that from below you can bound your B of U and U from below by alpha times U squared, and from above you can bound it by CB times U squared, because if you plug in to the bounded condition here u and u, then you also get u squared. So you see that those two quantities are bounds from below and above, so that if you have both of them fulfilled, then you see that the value of b of u and u is kind of from both directions bounded by the norm. And that tells you, firstly, that as long as the norm is not going to infinity, your b will also not go to infinity. And as long as your norm doesn't become zero, your b is also not zero. So you kind of have two limits, from below such that it's actually bigger than zero, and from above such that it's not infinity. Okay, so we have those three properties here, and that's all we need in terms of theoretical discussion of those bilinear and linear forms. And now we can continue with the result that we're interested in. The result we are interested in is the so-called lemma of Lax-Milgram. So in order to start the discussion, we will dive right into the strictly mathematical formulation, and afterwards we want to look at the use for us. Okay, let's start. The lemma of Lax-Milgram talks about Hilbert spaces. So we say that let V be a Hilbert space. Okay, so we can always have in mind that we're talking about H1, for example. And then we want, if B is a bilinear form, so mapping from V times V into the real numbers, if that is a bounded and coercive bilinear form, and L, which maps from V into the real numbers, and L is a bounded linear form, the problem, now here we want to write down an abstract variational problem, that's what it's called. The problem, find U in the space V such that B of U and V equals L of V for all V in V. That problem has a unique solution. Okay, let's look into this. What do we need here? We need a Hilbert space. Okay, we are on H1. Always when we talk about this in the following, we talk about the space H1. Then we need a bilinear form that is bounded and coercive, and we need a linear form that is bounded. And then this problem, finding U in our space such that the bilinear form of U and V equals the linear form with V for all test functions in V, has a unique solution. And this is the important part. So this problem has a unique solution if we can fulfill the boundedness and the coerciveness for B and L. Okay, this sounds very theoretical, but if you look at this problem that we have written down in green here, then you can already see that this kind of looks like our partial differential equations in weak form. Because whenever we talked about them, this was something like find U in H1 such that some integral is equal to the other integral for all V in H1, something like that. So yeah, this is the abstract setting, but let's look at it a bit more in detail. And for this, I want to give you a guideline how to use this. So in order to use Lax-Milgram's lemma, you need to bring your PDE into a form that is, well, applicable for this setting. So we need to bring our PDE into the right setting. And the first step is always to derive the weak form. That is something we have talked about before. Is step one, I would say. And now let's look at the weak form of Poisson's equation with homogeneous Dirichlet boundary conditions. So the simplest thing we had talked about before. That read something like find u in h10 of omega, here h10 because of the homogeneous Dirichlet boundary condition, so 0 on the boundary, such that and then there was this integral over omega of gradient of u times gradient of v that resulted from taking your Laplacian, multiplying with the test function, and then applying the Gaussian theorem to kind of do partial integration and reduce the number of derivatives on u, such that gradient of u times gradient of v is equal to an integral over f times v for all v in v. And now if we look at those, of course not v in v, but v in h10 of omega. And if you look at this, then this contains all the ingredients we need for the Lax-Milgram lemma. We only have to take it out in the correct way. So first thing, Lax-Milgram talks about some abstract Hilbert space V. Okay, H10 is an example for a Hilbert space. So we can simply take this here, and this is the part of the problem formulation in Lex-Milgram's lemma. So we say V is H10 of omega. That's a Hilbert space. That's perfect. Then in this problem here, on the left-hand side, we have an integral over gradient of u times gradient of v. This is a bilinear form that can easily be checked because the gradient and the integral are both linear operators. So this is linear in both u and v. So we can simply take this out here and say this is b of u and v. And on the right hand side here, this is a linear form because for some fixed f, this only has variable v. And this is also linear, of course. Okay, so then we can also take this part here out, and this is called L of V. So we see that we are already in the correct setting for Lax-Milgram's lemma if we have our weak form of the PDE. And yeah, let's summarize what we have learned until here, because that's all the ingredients we need already. We only have to put it in the right way. So information one is that the weak form of a PDE is a so-called variational problem. All of these problems that are written in a form find something such that this and that is true for all of something else is called a variational problem. So number one, the weak form of the PDE is a variational problem. And the form is the right one that we need for Lax-Milgram's lemma. So it is a variational problem. Find u in the space V such that B of u and V equals L of V for all V in V. Okay. Then, number two, if it is possible to show that B is bounded, B is coercive, and L is also bounded, then Lax-Milgram's lemma gives us unique solution. So if, and let's use some colors here now, if B is bounded, then if F is bounded and if also B is coercive, if all those three properties are true, there exists a unique solution. And there is a reason why I've written this last property of coercivity in red, because this is usually the problematic thing. So usually when you have a well-defined problem, boundedness for B and F is not a problem, but coercivity is. And that's what we will later on see. And the last step is something in between the summary and the outlook, the interplay between the PDE and the boundary conditions. Decide if this is true. So this is kind of the last thing we need to note at this point. The interplay of the PDE and the boundary conditions decide if that's actually true. And that's something that you probably haven't seen in ordinary differential equations that strongly. Because here in PDEs, when talking about PDEs, it's crucial to always talk about the boundary conditions. That's why I've been stressing this fact so much from the beginning, that we always need to write down in which space we are, which boundary conditions we talk about, because they determine if something has a unique solution or not. So you can't just write down the PDE because that doesn't tell you anything. Now, after discussing all those preliminary ideas of the general setting and the way this gives us the Lex Milgram Lemma, we now need to look at the actual practical examples. How does this look when we use it, or how does this help us? And for this, we simply start with the example 1, reaction diffusion problem. So we have a problem that is composed of the Laplacian here and some reactive term. That's something you've seen before. And as the first case, we talk about the Dirichlet boundary condition. So we take this simple problem and put in homogeneous Dirichlet boundary conditions. That's not very problematic. Okay, let's start with step 1, because that's what we've said before. Step 1 is always the derivation of the weak form. So step 1, we need to derive the weak form, and I will do this a bit quickly because we have seen this before. We start by multiplying this whole thing with a test function v and integrating over the domain omega. So minus integral over omega, not 2 minus, just 1, Laplacian of u times v plus lambda times the integral over omega of u and v equals the integral over f times v. Then we apply the Gaussian Theorem for the first integral, and this gives us an integral over omega of gradient of u times gradient of v plus lambda times the integral of uv equals integral over f times v. And because we have Dirichlet boundary conditions, so first thing we need to note here is, maybe I can go back one step. When applying the Gaussian Theorem, you always have those boundary integral parts, and they have vanished because v is in H10, v is 0 on the boundary, so that's why we didn't need to take care of that. Okay, so that's your weak form. Maybe I can write this as an intermediate step. So this is integral over omega of gradient of u times gradient of v minus an integral over the boundary of omega of gradient of u in normal direction times v plus lambda times the integral over u times v equals the integral over f times v. And here this part is 0 because v is in H10, so this whole integral vanishes on the boundary. So we arrive at our problem that we need to find u in h1 0 of omega, such that the integral over omega of gradient u times gradient v plus lambda integral uv equals the integral over fv is true for all v in h1 0 of omega. And as before, we now need to identify, so we have already identified our space. The space is h1 0. That's something important here. h1 0 is our space. And the other things we need to identify are the bilinear and the linear form. And the bilinear form is simply the left-hand side of that weak form. So it's an integral over omega of gradient u times gradient v plus the integral over, or lambda times the integral over u times v. And that linear form is just the right-hand side. So that's the integral over f times v. Okay, and now if we want to apply Lax-Milgram's lemma to find out if this has a unique solution, what do we need to show? Well, we need to show that both b and L are bounded on h1 0. And we also need to show that b is coercive on h1 0. So now let's do this. Step 1, we want to show that b is bounded. That's not so difficult. For this, we start on the left-hand side by writing down b of u and v. B of u and v is in the definition just the integral over omega of gradient of u times gradient of v plus lambda times an integral over u and v. And the first thing we need to apply here is the Cauchy-Schwarz inequality. That tells us that if we have a product that is integrated, we can bound this from above using the norms. Meaning that if we use the Cauchy-Schwarz inequality, CSI, that's kind of a fancy abbreviation, this gives us the norm of u, the gradient of u in L2 times the norm of the gradient of v in L2. So that's those two parts from here, plus lambda times the norm of u in L2 and the norm of v in L2. Okay, that's all good and nice for now, and we are doing 2 steps now. The first step is we take the constants out. So we bound this from above by a new constant that is the maximum of 1 and lambda, because 1 is a factor that's written here and lambda is the factor that's written here. So if we take the bigger one of those, we are definitely not making it smaller. And then I take those brackets with the stuff that were already here. So I'm putting all of this into those brackets. So nothing has changed, only the constants. And now we want to make this even bigger by adding new non-negative terms. So I'm keeping this constant. I'm also keeping my 3 points. So those parts that we have written down here already are also kept. And I'm adding some more terms. I can always do that because I'm just doing an estimation and making stuff bigger by adding something that is non-negative. As long as I'm adding something that's non-negative, I will definitely not make the stuff smaller, so my inequality is still true. And what I'm adding here is gradient of u in L2 norm times v in L2 norm. Okay, that's kind of the product of this part and this part. And the last thing I'm adding is the L2 norm of u times the L2 norm of the gradient of v. Kind of some mixed products here. And probably you can already guess why I did this, because now we have all the summation parts that we need. Because now this reads maximum of 1 and lambda, just like before. And now this is norm of u in L2 plus norm of the gradient of u in L2 times norm of V in L2 plus norm of the gradient of V in L2. So I kind of have just, and if you want to multiply this out, you would get your two parts that you had already here plus those other parts that I've just artificially added. And now this is perfectly fine, because this now is what I wanted to have. So this is the H1 norm of U, because it has the L2 part and the gradient part, times the H1 norm of V. So you see here we have taken the Cauchy-Schwarz inequality and applied some mathematical tricks by taking the maximum of the constants and adding something non-negative, and that gave us exactly the thing we wanted, because this thing here is now called CB, so that's just some constant, and we are completely happy because we can bound our bilinear form from above by some constant times the product of the two norms. And the next step is to look at the boundedness of L. The boundedness of L is much simpler actually, but it's done in the exactly same way. For this, we write down L of V, and that's just an integral over omega of f times v. Then I can write down and apply the Cauchy-Schwarz inequality. That gives me the L2 norm of f times the L2 norm of v. Now, the L2 norm is always a part of the H1 norm. So if I'm adding something to my L2 norm, I'm just making stuff bigger. So I can just replace the L2 norm by the H1 norm. And that's that, because this f is just a part of the problem, so I can just call this CL, and then I'm done. So L is bounded. And the last part here is the coercivity of B. B is coercive. And for that, we write down a similar thing. We write down B of U and U. So now you put in the same argument in both components. What does that mean? That's an integral over omega of the gradient of U squared plus lambda times the integral over U squared. And now we want to bound this from below, so we have to estimate in the other direction. So instead of taking the maximum of the two coefficients, I'm taking the minimum. So I'm bounding this from below by the minimum of 1 and lambda, and this summation of the two integrals. And then I'm almost done already, because this part here already is my H1 norm squared. So this is just minimum of 1 and lambda. And this here is just the H1 norm of U squared. And that's precisely what we wanted to show, because if lambda is bigger than 0, then this minimum of 1 and lambda is also bigger than 0, and then we can call this thing here alpha, and we see that B is coercive. And now with the combination of those three quantities, we are done, because we can now conclude that the reaction diffusion problem with our homogeneous Dirichlet boundary conditions has a unique solution, following from Lex Milgram's lemma. So with Dirichlet, boundary conditions has a unique solution. And you might ask at this point why it was important to talk about Dirichlet boundary conditions. Well, let's look at the the case of Neumann boundary conditions. So let's see what does actually change when we go to the other boundary conditions. So we now have gradient of u times n equals 0, and we start with the same step 1. We again need to derive the weak form. And the weak form now is again derived by multiplying the whole thing with a test function and integrating over omega. So I'm again arriving here. And now we again need to apply the Gaussian Theorem that gives us gradient of u times gradient of v plus the boundary integral, gradient of u times n times v plus lambda u v equals integral over f and v. Now we are not longer talking about Dirichlet boundary conditions, so we no longer know that v is 0 on the boundary. So we can't just vanish the boundary integral because of v, but we see that u, the gradient of u in normal direction, is 0. So this boundary integral vanishes again, but this time because of the first factor and not because of the second one. So this vanishes again, and we again arrive at the same bilinear and linear forms as before. So let's write down the weak formulation. We want to find u in, and now we are not longer searching in h10, but only in h1 of omega, such that the integral over gradient of u times gradient of v plus lambda integral over u times v is f of v for all v in h1. Okay, you see here that the bilinear form b of u and v hasn't changed from our previous consideration, so that's still gradient of u times gradient of v plus lambda integral over u and v. The linear form also hasn't changed, so that's also still the integral over omega of f times v. And yeah, so what has changed? What's changed is only the space that we are interested in. So now we're talking about h1 of omega and not h10. But in this particular case, if you think back into the proof of showing that B is bounded and coercive and L is bounded, there we did not really use the fact that we have those homogeneous Dirichlet boundary conditions anywhere. So we did not use any of those particular properties of h10. That's why we can do all of those proofs just like before. That's why I'm not doing this again. So you can take a look back and see that nothing has changed because we have the same weak formulation. So we have the same B and the same L. That's why we can again conclude B is bounded. L is bounded. And also the problematic property B is coercive. It's not problematic here. So in total, you can put all these properties together and say that the reaction diffusion problem with homogeneous Neumann conditions, sorry about that, the reaction diffusion problem with Neumann boundary conditions has a unique solution. Okay, right now I have probably not made you puzzled with my strong underlining that the boundary conditions are so important here, but you will see this in a few minutes. So we again here have a unique solution. That's pretty nice. And you can try to verify that the proofs for boundedness and coercivity are just the same as before. And the other important example that I want to show you today is Poisson's problem. So that was kind of the simpler equation, but you have seen in example 1 that everything goes super smoothly when you talk about the reaction diffusion problem. That's why I've chosen this as the first example. And as you can already guess, it's not going to be that smoothly here in Poisson's problem. So we start again with the Dirichlet boundary conditions. And I'm not going to do the derivation for the weak form here, because that's something we have seen many times throughout the semester. So we can just write it down. So we want to find u in h1 0 of omega such that, and now here on the left hand side we have gradient of u times gradient of v equals an integral over omega of f times v for all v in h1 0 of omega. Now here your bilinear form b of u and v is again the whole left hand side, but we are now missing this part with a lambda. So that's just an integral over omega of gradient u times gradient v, and then the right hand side linear form is L of v equals integral over omega of f and v. And the space is again our space h1 0. And then let's see what happens here. If we proceed, we can start by looking at the boundedness of the bilinear form. So we can see that B is bounded. For that, we start just like before. B of u and v. That's the integral over gradient of u times gradient of v. Then we again use the Cauchy-Schwarz inequality. That gives us that this is smaller or equal to gradient of u in L2 times gradient of v in L2. And well, if we just add the L2 norms of u and v to this, we are still just making it bigger. So we can just write gradient of u in L2 plus the norm of u in L2 times, and then that part that we already have, plus something non-negative that we are adding. And that gives us the norm. So this part here of bounding this from above by the h1 norm of u times the h1 norm of v, that part is actually simpler than before, because here we didn't even have to pull out any mathematical tricks. If you look at the linear form L, then you observe that nothing has changed here. So it's exactly the same linear form. So L of v is still this thing. And then that's why I'm not doing any proofs here. So we can already see that this is, we have already seen this is smaller or equal to some constant times the h1 norm of v here. So I'm not doing anything here. Okay, so this all goes pretty smoothly. And here comes the reason why I've mentioned before that this coercivity is actually the problematic property. So now let's see that B is coercive. And for that, we start as usual by plugging into the B those same arguments, B of u and u. That's an integral over omega of gradient of u squared. That's beautiful. And that is, if you think about it, just the gradient of u in the L2 norm squared. And now you have a problem, because you want to bound this from below by some constant times the H1 norm of U. But the H1 norm of U consists of the L2 norm of U plus the L2 norm of the gradient of U. So the problem that you see here is that you want to bound this term, the L2 norm of the gradient of U, from below by itself plus something non-negative, which is probably not 0. So this simply, in this case, doesn't work. So you can't just do this. Okay, we have a problem now. Because this looks as if we couldn't prove coercivity. But on the other hand, you have seen solutions for this problem many times. I've shown you these perfectly beautiful bulb-shaped membranes for the Poisson's problem with homogeneous Dirichlet boundary conditions many times. So it appears that there exists a unique solution, but we can't prove it like this. So the core point here is that I cannot use the gradient of U in L2 norm to bound these function values from above. That's in general not true. And for that you can verify a simple example. If you set U to the constant 1 function or any other constant function, so let's say U is the constant 1, then the gradient of U is the constant 0. That's why the L2 norm of the gradient of U is also 0. And that's why it's in no way doable to use this to bound the L2 norm of the function U from above, because the L2 norm of U is something like the magnitude of the domain. So it's not possible to find any alpha such that this is bigger or equal times of alpha times the norm of U in L2. That's just not doable. But we need to do it somehow. So the solution for this is a famous mathematical inequality called Friedrichs Inequality. That's kind of variant of the Poincaré inequality, and let's write it down what it tells us. So there exists a constant, and we call it CF because it's the constant from Friedrichs inequality. So CF bigger than 0 such that the L2 norm of U is bounded from above by the constant times the gradient of U in L2 for all, and here comes the important and interesting part, for all U in H1 0 of omega. Okay, what does this tell us? Well, this essentially tells us, in the case that we have just considered, where we talk about functions in H1 0, there it's actually possible to bound the function from above by the gradient. But this is not intuitively clear. So let's give some remarks about this part. The first part is the Dirichlet boundary condition. So the fact that we are in H1 0, this is very important here. Okay, so the Dirichlet boundary conditions are a crucial ingredient, because if we don't have them, we simply don't have any control over the function values. Okay, that's kind of the whole idea. When you can control the gradients, because that seems to be the case here on the right hand side, and you also can control the function values on the boundary, then you have control over the function values too. But if if you look at this or imagine this in some simple one-dimensional setting, if I have an interval from here 0 to 1, and I know how fast my function is increasing, and I also know that it's 0 here and 0 here, then I can compute how fast, how big the solution values can be. If I know that I'm starting at 0 here, then I know how strongly I'm increasing, but I also know that I'm going back to 0 here, so it can't infinitely rise. Also, the counter side of this is that on h1 of omega, this is in general not true. And the counter example for this is simply the example with u to be equal to the constant 1. Because this constant 1 function obviously doesn't fulfill this inequality, but this is not an h10 function. That's just an h1 function. So there you can see that this is a simple counter example why this can't work in h1, but it does work in h10. And now let's go back to our Dirichlet boundary conditions in Poisson's problem. And the step where we were was that we had b of u and u equal to gradient of u squared, which was just the L2 norm of the gradient of u squared. Now we take a little mathematical trick here, and we split this thing into two. We split this thing into two equal halves. So far we have not changed anything. This is just a mathematical reformulation of everything. So obviously if you would add them again, you would get your one norm. Then you apply Friedrichs inequality to one of those two parts. So here it's Friedrich. And then this gives you that you can bound this from below by the function values, so the L2 norm of the function values. So this is 1 over 2 times CF times the L2 norm of u squared, plus, and then this other part just stays the same as it was. And then you can use the minimum trick again. So you can use this, you can bound this from below by the minimum of 1/2 and 1 over 2 times CF and the H1 norm of u squared. So you see here, with a little trick and Friedrichs inequality, we can actually prove that this bilinear form for Poisson's problem is coercive on H10, and that's very, very important here because Friedrich only holds on H10. So our experience that this simple problem of Poisson's equation with homogeneous Dirichlet boundary conditions has a solution, that's true. We just couldn't prove it in the beginning, but now we can using this famous inequality. So we can conclude here Poisson's problem with homogeneous boundary conditions, homogeneous Dirichlet boundary conditions, has a unique solution. And that is again a result from Lex Milgram's lemma. And in order to prove coercivity for B, we had to use Friedrichs inequality. And then the last step is to look at the Neumann boundary conditions here. And I'm not spending too much time on this. So the weak form is simply given by find u in h1 of omega, so not h10, it's h1, such that the integral over gradient of u times gradient of v equals the integral over f times v for all v in h1. So b and L are just the same as before, but now our underlying space is h1. And then if we look at the individual properties, we can still say that B is bounded, because that proof using the Cauchy-Schwarz inequality works just like before. We can also say that F is bounded. That's also something that always works, but B is not coercive. And not only is it not possible to prove coercivity because Friedrichs inequality doesn't hold, but also it's just not possible. So you can prove that it's not coercive. And the counterexample, y, is simply again plugging in a constant function. Because if you plug in b of the constant 1, then this is plain and simple 0. If you take the gradient of the constant 1 function, that's 0. And there is no way that you can bound this from below by some positive constant times the norm of this one function. So it's just not coercive, and that means you can't use Lex Milgram's lemma. Okay, some might argue that there is some other result that would give us unique solvability, but if you think about it more in detail, and I will leave this as an open question here, you will figure out that it's just not doable to compute a solution in general, and the concept is quite close to what I've done initially with the one-dimensional example. So that's essentially trying to solve Poisson's problem with Neumann boundary conditions. So you have already seen that it doesn't work. Okay, so we have now seen how this goes down. And that's almost it for today. We just want to summarize this for a bit. So we have two columns here in this schematic. The left column is Poisson's equation and the right column is the reaction diffusion problems. The upper row are Dirichlet boundary conditions. So you see Poisson's problem with Dirichlet boundary conditions works perfectly fine. The reaction diffusion problem works just as well. But then if you switch to Neumann boundary conditions, you have a huge difference because the reaction diffusion problem gives you this beautifully shaped thingy there, while Neumann simply doesn't work for Poisson's equation. And the whole reason is also quite intuitive to understand. The hand-waving argument behind this concept of coercivity is that you need to control your function values somehow. If you can control them with boundary conditions, it's fine. If you can control them with the equation itself, and that's the case here, because here you have function values in your equation, then that's also fine. But if you have this problem here, where you have no control over the function values, because you only talk about derivatives, then it doesn't work. That's kind of the take-home message of these examples here. So let's conclude. In the field of PDEs, even when handling them numerically, it's very important to always know if a solution exists and if it's unique. Otherwise, you run into these terrible problems that we have seen here when talking about the Neumann boundary conditions for Poisson's problem. The weak forms that we have already considered for PDEs are already in the form of a variational problem in abstract Hilbert spaces. You have to just look at them correctly. The Lex Milgram Lemma provides a tool for analyzing existence and uniqueness for solutions of variational problems. In order to apply it, you have to prove boundedness for the linear and the bilinear form and the coercivity for the bilinear form, which is the more problematic deal. And yeah, whether or not you have a solution depends on the combination of the PDE and the boundary condition. And with this, I thank you all for your attention for this lecture, and I hope you could follow me about the solution theory.